Today we're going to learn about integration by parts. This technique is useful for integrating integrands involving products, especially products of polynomials and transcendental functions. Now, just in case you don't remember, transcendental functions are functions like our exponential functions, our logarithm functions, our trig functions, our inverse trig functions. Those are all examples of transcendental functions. So we have those times by a polynomial. We probably want to use integration by parts. Now, when we're doing integration by parts, the formula is going to have a u, a v, a du, and a dv. So you want to be able to choose your u and your dv easily. So you're going to make du if du is simpler than u, and you want dv to be easy to integrate. So you can find your v. Integration by parts can be in many combinations. There's a number of combinations that are very popular and that you kind of want to be able to recognize. So our first one, if I ask for the integral of x to a n power times sine of something, like sine of ax. So I have a trig function times by a polynomial. I could use sine or cosine. Or if you have a polynomial times an e to a power. If you have these three situations, what you're going to let your u be is you're going to choose u to be the polynomial, the x to the n, and then you're going to choose your dv to be the other function, the sine of a to the x, the cosine of a to the x, or e to the ax. So just remember, if it's a polynomial times a sine or cosine, or a polynomial times e to a power, let u be the polynomial. The next type that you'll see, if you have an exponential e to the ax times a sine function, or an exponential times a cosine function, in this case, you're going to choose for your u to be your trig function, either the sine of b of x or the cosine of bx. And you'll let your dv be your exponential function, e to the ax. The last popular situation you're going to have is if you have the integral of a polynomial times a natural log, integral of a polynomial times an inverse trig function, mainly inverse sine or arcsine, and a polynomial times your arctangent functions. If you have one of these situations, you're going to let your u be the logarithm function, the arcsine function, or the arctangent function. This is one of the few cases where u is not going to be the polynomial. In these two spaces where you have a polynomial times a natural log, an arcsine or arccosine, your dv will be the polynomial, x to the n. All right, so what's this formula I'm talking about? Why am I talking about u's, v's, and dv's and stuff like that? Well, the integration by parts formula is something you're just going to have to memorize. It is the integral of u times dv is equal to uv minus the integral of v du. So when we have two products multiplied together, our integration is going to be u times v minus the integral of v du. So let's look at our first situation here. We have the integral of x natural log of x dx. So I have a polynomial times a logarithm, natural log. So that means my u is going to be the natural log. Well, I take the derivative of the natural log. That gives me 1 over x dx. So that's my du. My dv is my other function, which is x. I integrate x. So the integral of x is 1/2 x squared. And so that's going to be my v. So now I'm going to use my formula, uv minus the integral of v du, and substituting in my given information. So in place of the u, I'm going to plug in the natural log of x. In place of the v, I'm going to plug in that 1/2 x squared minus the integral of 1/2 x squared times my du. I'm going to replace with 1 over x dx. All right, let's simplify. So the first term, I really can't do anything with it. It's just going to be x squared over 2 times the natural log of x. And then here we can cancel out an x and make that and bring out the 1/2. And we get 1/2 the integral of x dx. See how easy that is to integrate? So the integral of x we know to just simply be 1/2 x squared. And then we simplify and add our plus c. And our final answer is going to be x squared times the natural log of x over 2 minus x squared over 4 plus c. Sometimes you'll see it written as you factor out your GCF of 1/4 x squared to get 1/4 x squared times 2 the natural log of x minus 1 plus c. Okay, in this next situation, we're going to look at, we have the integral of x squared e to the x dx. So I have a polynomial times an exponential, so I'm going to let u equal the polynomial x squared. So the derivative of that is going to be 2x dx. And then my dv has to be e to the x. And so when I integrate e to the x, I get e to the x. That's my v. So again, we're going to use our formula, and we take our u times our v minus our integral of our v du. Now we notice that here in this integral, when I factor out the constant 2, I still have a product of e to the x and x. So I have another u, and again, I'm going to let that be the polynomial, and the derivative of x is 1. And then my dv is going to be the exponential e to the x, and the v, so the integral of e to the x, is also e to the x. So copy down what I have, and then in brackets, I'm going to now take the integral of e to the x by using our integration by parts formula again. Don't forget to distribute the -2 to each term. And when we integrate, so now we're just left with the integral of e to the x, which we finally can figure out. That's no longer a product. And so our final answer will be x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Again, you can factor out your GCF of e to the x, and that'll give you x squared minus 2x plus 2 plus c. Okay, in some problems, you'll have so many repeating of the process, or when you have a repeating of the integration by parts, there's a technique called the tabular method that makes it easier to work with. This is especially helpful in those first 3 forms that we talked about on the last page, when we have the polynomial times sine function, a polynomial times a cosine function, or the integral of a polynomial times a exponential function. When you have these 3 situations, it's very useful to use the tabular method. So I'm going to show you how to set up the tabular method through this example, the integral of x squared sine of 4x dx. Okay, so again, we're going to start by identifying our u and our v, and we're going to set up our table. Our first column is going to be the sine, and this is going to alternate from positive, negative, positive, negative. Our second column is going to be our derivatives, and our third column is our integrals. So our derivatives, that's our u du. So we're going to look at our 2 functions that are multiplying together, and we're going to identify our u term. And so in this case, remember, when you have a polynomial times a sine function, you'll make your u your polynomial. So I'm going to let u equal x squared. And then I'm going to keep taking the derivative of this x squared until I get 0 as an answer. So it took me 3 derivatives to get to 0. Okay, then you're going to take your dv term, which is the other term in our function, in this case sine of 4x. And that's what's going to be our first entry in our integral column. Now we're going to integrate this as many times as I differentiate it. So in this case, I need to do 3 integrals. So I'm going to take the integral of sine of 4x, and that gives me negative 1/4 cosine of 4x. Now I'm going to integrate that, and it gives me negative 1/16 sine of 4x. And then one more time, I'm going to integrate that, and it's going to give me negative 64 cosine of 4x. Okay, so our signs always start with positive, and we just alternate for as many rows as we have. Now here's the cool part. The sine and the derivative go straight across, then you diagonal down to the integral. And you're just going to multiply those together. So I got positive times an x squared times a negative 1/4 cosine of 4x is going to be my first term in my answer. And then I'm going to go across and diagonal for our next entry. So that'd be negative times 2x times a negative 1/16 sine of 4x. And then our last term, again, we're going to go across and down. So that's going to be a positive times 2, so plus 2, times by 1/64 cosine of 4x. And I know I'm done when I run out of integrals. And so now the only job is to simplify to get negative x squared over 4 cosine of 4x plus 1x over 8 sine of 4x plus 1 over 32 cosine of 4x, and then don't forget your plus c. All right, let's look at our next problem, the word problem. The estimated rate at which oil will be produced from a certain oil well T years after production has begun is given by R sub T is equal to 100 TE to the negative 0.1 T thousands of barrels per year. Find an expression that describes the total population of oil at the end of the year T. So this is a way to apply this integration process. So we need to figure out the total production of oil at the end of the year. So we're going to let T of T be the total production of oil at time T is greater than 0. Now we were given the rate, the estimated rate in which the oil was produced. So we have the rate of change of the amount of oil. So basically we have T of T's derivative. So the derivative of our total production of oil is equal to our rate of oil production. And so we can say that's equal to that function, that R sub T function given in the problem. So they gave us the derivative, and we want to find the original function. Now remember, if you're given the derivative, you want to find the original function, your job is to integrate. So we're just, our entire problem here is to find the integral of R of T. But the problem lies that this is a product of two functions. Well, first thing I factor out the 100, and it's a product of T times the exponential e to the negative 1.1 T. So I need to do my integration by products rule here. Let's do the tabular method just so we can practice with it. So I'm going to set up my table here. Now remember, our first columns are signs, second columns are derivative, and it's going to be our polynomial. So it's T, derivative of that is 1 and 0. Then our last columns are other function, and we're going to integrate each of these. So the integral is going to be negative 1 over 0.1 e to the negative 0.1 t, which will simplify down to simply negative 10 e to the negative 0.1 t. And then we integrate that. We end up with simply 100 e to the negative 0.1 t. And then go back to our first column, put in our signs. Remember, the signs alternate. Positive, negative, positive. And so when we go across and down, this will end up being T times that negative 10e to the negative 0.1 T. And then minus times by, and again, we're going to go over and down, over and across. So times by 100 e to the negative 0.1 t, and that all is times by the 100 I factor out at the beginning. Don't forget that 100 we factor out at the beginning. So that gives us a negative 1,000 e to the negative 0.1 t times t plus 10, close that parentheses, plus c. And that's if I find I took out my GCF. I skipped a few terms there. But that's my T of T.